the context of this, Maria, she was an Humboldt State University graduate and a Redwood Energy staff person for a period of time, and did a lot of deep research on how the software works to predict water heaters. And then she went to Integral, which is a large engineering firm, did tons more modeling work. And I've asked her to, this is for the geeks and the energy modelers in the crowd. I understand that not necessarily for everyone, but to understand this modeling in a more granular level, sort of like a training. If you'd like to understand how to do energy modeling in California, this is the residential side of it, our current software. So Maria, thank you so much for showing up and teaching us. Take it away.
Thank you, Sean, and thank you everyone for being patient to the last presentation. Can you hear me, by the way? Fine?
Yeah, you sound perfect.
Okay. So again, today's presentation is going to be on all electric modeling in CBECC-Res 2019. So this is an outline of what I'm going to be presenting today, briefly. I know we're running out of time. First I'll be talking about what changed in CBECC-Res 2019 .1.3 version. And then I'll introduce a little bit about the project that we used for this analysis, that is the Sunnyvale Edwina Benner Plaza multifamily project. This project includes a central domestic hot water heat pump water heater system. And I will be showing you very briefly how to model it in CBECC-Res 2019. And then the second part of the presentation would be comparing the proposed design, that is our Edwina Benner Plaza project versus the standard code design. And we'll be looking at the energy use for both proposed in the standard design. And then we will also look a little bit into the model, the proposed model, and compare it to field data for hot water use.
Buckle up, it's gonna be awesome.
So for those of you that do not know what CBECC-Res is CBECC-Res 2019 is used to show compliance with the performance approach of the 2019 California Residential Building Energy Efficiency Standards. A few of the reasons why we use the 0.1.3 beta version is for the following bullet points that are on the left. It includes new features such as ESMA neighborhood solar shares, improved multifamily central heat pump water heater capabilities, and new HVAC equipment types, including packaged terminal heat pumps. On the right, we have a screenshot of all the features that the new version includes and highlights all if you want to take a look at it. So a little bit about the Sunnyvale Edwina Benner Plaza. It is an all-electric building. It's a 4-story multifamily apartment building located in Sunnyvale, California. First floor consists of non-residential spaces. Floors 2, 3, and 4 are residential spaces. The building is separated into 3 wings. I would say wing 1, wing 2, and wing 3. And for mechanical systems, we have, for HVAC, we have split heat pump systems serving each unit. And then we have a central domestic hot water heat pump water heaters serving the building. Our main focus and our goals for this, just for this analysis, for this part of the project, we have energy, we created an energy, well, actually 2 energy models for wing 1 and wing 2, and then 1 for wing 3. We mainly focus on just the residential part, that is floors 2, 3, and 4, mainly because we wanted to use CBECC-Res. And the reason why we wanted to use CBECC-Res is because CBECC-Res uses the California simulation engine. And for a research project, we're focusing in diving into this California simulation engine and what it's doing. So for this analysis, we didn't model the non-res part, and we just modeled the residential spaces. As I said earlier, we created 2 separate models because there's 2 central domestic hot water heat pump water heater systems. One is serving wing 1 and wing 2, and the other one is serving wing 3. And then finally, our goals is to determine the overall performance of the building with this 2019 code. And then another of our goals is to evaluate the performance of the newly added central domestic hot water, heat pump water heater in CBECC-Res 2019. And then finally, we want to look at the model versus actual field performance. So briefly, our central domestic hot water heat pump water heater system, we have one serving wing 1 and wing 2, and then one serving wing 3. Our heat pump water heater type is a Sandin CO2 system. Wing 1 and wing 2 have about 12 compressors serving wing 1 and wing 2. We have 3 tanks that are about 500 gallons. We have a loop tank, it's a ream loop tank, and we have that is about 80 gallons volume. And for wing 3, we also have the heat pump water heater type is a Sandin CO2. There's 4 compressors serving the wing. We have 1 storage tank. It's about 500 gallons. And again, we have a ream for the loop tank, and the volume is about 80 gallons. So now I'm going to show you how we modeled this in CBECC-Res. For those of you that have never used CBECC-Res before, I will only be showing you how to model the domestic hot water side. If you're interested in learning more how to build a model, we can talk later. Here we go. So once you start building your model, your building tree, you have an envelope side, and then you have a mechanical tab. Under your mechanical tab, you want to select the mechanical tab and then right-click on the project. Then you'll have a drop-down that says create. You want to create domestic hot water system, and you'll have a pop-up screen that says create domestic hot water system. So then you'll name your system, press OK, and then the next window that will show up is the one on the left side. It shows the tab, the domestic hot water system data. So this is how it would look, empty. Since we're modeling the central water heating, we want to make sure that we check that. And then if you look at the right side, the screenshot shows that the central water heating is checked. In our case, we have a heat pump water heater, so we have that selected. And then you want to select your distribution type. The next thing you want to do is go on to the central heat pump water heater tab. This is where we get to input all our inputs for our system. And then this is where the new features come in for the heat pump water heater. As you can see, highlighted in yellow, we have a drop-down menu. And then the drop-down menu is showing on the right. We have a large variety of selections for the compressor type. In this case, we have the Sandin. We selected that for compressor type. We put in all our inputs. And now for the central heat pump water heater loop tank, since the drop-down menu does not have the ream, we selected Sandin as just to be the closest to what the ream will be. Finally, we want to make sure that our recirculation loop tab is filled out. Make sure that your number of recirculation loops is in, the number of insulation thickness, and so on. So now we created our central domestic hot water system, but we need to connect that to our dwelling units. Otherwise, it won't run, or you'll just get a bunch of errors. So going back to the envelope tab, we have to connect the system to our dwelling units. So in order to do that, you go into the envelope tab, scroll down into a folder that says dwelling unit types. And then in this case, I'm just selecting one unit, unit 227 type 3AC. And then when selecting, this screen will pop out. This is dwelling unit type data. At the bottom, you have your water heating system, and you select your domestic hot water system that you created. So once we have, our systems, in our HVC, our domestic hot water, our envelope constructions in, we created a model, we run it, and then we have energy results. We have our proposed and our standard results. So at the very end, the model will generate a summary of energy use. On the left, we have wing 1 and wing 2 model, and then on the right, we have wing 3, the overall energy usage. And as you can see, it is split between, so we have the standard design on the left and the proposed on the right. And the main energy uses that are shown is space heating, space cooling, indoor air quality ventilation, and water heating. Just looking at wing 1 and wing 2 for now, we can see that, there's space heating, space cooling, indoor air quality ventilation is complying better than code. And we can see that through like the TDV values. The proposed design is much lower than the standard, and therefore we have a positive compliance. But we do notice that we have a water heating compliance is our proposed design is complying less or worse than standard by negative 0.129. Overall, is the entire model is passing by 15.5%.
But can you explain a little bit why are we getting negative compliance on the water heating that you just set up? It's a sand-in after all.
Yeah, so that's something we decided to look into. That's something I'm going to go into next. And we noticed that it happens in both wing 1 and wing 2 model, and then wing 3. So one of the things that we noticed that in the standard design, the water heating is using there's natural gas energy being used. So when we looked into the standard design system, it is our proposed domestic hot water system is being compared to a large instantaneous natural gas water heater, and a large portion of the energy is in therm. So we decided to look at the overall energy of the building. So that is adding up wing 1, wing 2, wing 3 for our proposed design, and see where the energy is being used. So we notice, so this is a graph of the average hourly energy use of the entire building for our proposed design. Of course, there's energy being used throughout the day, like there's some, between 7 and 3 p.m. and then again later at night. But we noticed that there's energy being used really early in the day, like between 1 a.m. and 6 a.m. And so there's some, we wanted to figure out what is causing that. So we decided to graph domestic hot water, proposed design domestic hot water energy breakdown. The energy breakdown includes the primary system. It includes the domestic hot water loop pump and loss makeup, and it includes the domestic hot water recirculation loop temperature maintenance. This is a graph of the average hourly energy breakdown. And so, as I mentioned earlier, like that there's energy being used between the hours of 1 and 7 a.m. And now we know that there's the domestic hot water recirc loop is turning on at between that time and using up energy. So furthermore, we wanted to look into we know that this is one drive, like that's causing the domestic hot water to use more energy. But we also wanted to look at TDV. So we looked at, so first of all, TDV is a code compliance metric. It incorporates societal and environmental impacts into the cost of energy during the given hour of the year. We took the overall energy use of the building for both the proposed and the standard, and we determined the TDV values by taking the 8760 data and multiplying it by a TDV factor. That TDV factor depends on the climate zone and the fuel type. So this is how we were able to get the proposed TDV values and the standard TDV values for the whole per month. And we noticed that the proposed design has low TDV in the colder months, but is higher in the hotter months. So, but overall, when looking at the total annual TDV, the proposed design is still higher than the standard. So we just want
to clarify, is the standard a gas system?
Yes. So actually the standard is, but it also has some electricity energy. So it's a combination of gas and electricity, mostly gas. And again, when calculating these TDV values, there's a TDV factor for gas, natural gas, and a TDV factor for electricity. So
what we're seeing is basically it's saying using electricity during the summer is something that gives you a high TDV impact, even though the actual electricity consumption will be much lower in the summer. Like the system will be way efficient because it's warmer.
yeah.
But the TDV impact, because it's compared to gas, looks bad.
Yes.
Like for most of the year even, which is okay. So comparing electric to gas does make it look like there's more electricity being used, because there is.
Yes, yes. And another thing that I did forget to mention, that natural gas is cheaper than electricity, but and I think that that is incorporated in the TDV values, or the TDV metric. So that's something that is also to think about. So sorry. So then finally I have some field versus the model hot water usage. Just keep in mind that this is still a work in progress. So here we have field and model data. This is the total monthly hot water usage. We notice that the hot water usage throughout the month, the field data is much larger than the model. This is something that's very interesting, because I would expect that they would be almost the same. I mean, throughout the month, the beginning first 4 or 5 months, like the field data is really large. And like at the very end, they're almost the same. But we think that we have to look further into the software to see what or not the software, but the CSE, the California Simulation Engine code, to see what is doing in terms of like the domestic hot water. So the next graph is also pretty interesting, because I didn't expect this. There is a really large hot water use for the model between 6 a.m. and 11. And that is way larger than what the field data shows. So that's something I was like, that we are interested in knowing what the model or what the engine is doing, or how it's being modeled, the source code, how domestic hot water is being modeled in the CSE. Because it's pretty interesting that it's really large throughout between in the 7 and 11. And the field data shows it's much more like just gradually increasing throughout the day.
And so the previous graph, you showed us that the field data showed significantly higher consumption than what the model was showing.
Yeah.
Month over month in total gallons of hot water use, which is probably because they're assuming lower occupancy than apartment complexes actually have. Like apartment complexes will probably have almost an extra person per apartment.
Yeah.
The model assumes.
Yeah. So occupancy
That
is
next graph, the next one shows us that they're assuming a huge peak in the morning that doesn't show up, and our peak is actually in the evening. Oh, cool.
Yeah. And then just to note that the hot water usage, we directly took it from the CSE, not from CBECC-Res. CBECC-Res does not give you these the data, so we had to go directly to the CSE model and take this information. So just a side note. But that concludes my presentation, and I'm open to questions.